Welcome to Learn with us. This is the 21st lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about small signal or AC analysis of bipolar junction transistors. In your previous lecture, you derived equations of small signal collector current, small signal base current, and small signal emitter current. In your previous lecture, you also understood what is transconductance and you also studied about small signal resistances. What are the learning objectives of this lecture? In this lecture, you will understand what is voltage gain and you will also study about methods that are used for AC modeling. Now we will talk about the voltage gain. We know that the DC collector to emitter voltage is given by this equation VCC minus ICRC, and we call this equation equation number 1, and we know that this equation is derived from this equation of collector current, which is VCC minus VCE divided by RC. And if we rearrange this equation, we'll get this equation number 1. And here we are talking about instantaneous quantities. So the total collector to emitter voltage or instantaneous collector to emitter voltage is given by this equation VCC minus ICRC, and we call this equation equation number 2. As you can see here, this VCE and this IC, they are instantaneous quantities. From our previous lecture, we know that this instantaneous collector current is equal to DC collector current plus AC or time varying collector current. Now, if we substitute this value here in this equation number 2, we get VCE is equal to VCC minus IC plus AC collector current, and it is multiplied by RC. Now if we open this bracket, we get VCE is equal to VCC minus ICRC minus ICRC. Now as you can see here, this term is equivalent to VCE, which you can see in this equation number 1 as well. So if we substitute this value here, we get VCE minus ICRC. Now we know that this instantaneous collector to emitter voltage is equal to DC collector to emitter voltage plus AC collector to emitter voltage. It means if I write plus sign here, then this whole term is written in bracket with this negative sign. And we know that we write AC quantities in lower case with lower case subscripts. Okay, so if I write this AC quantity here, it is equal to minus ICRC. Now if you remember from your previous lecture, we studied one graph where I mentioned that slope was transconductance and it was equal to IC divided by VBE. Okay, it means this IC is equal to transconductance multiplied by this small signal base to emitter voltage. Now if I put this value of IC here in this equation number 3, I'll get VCE is equal to minus GM VBE RC. Okay, now if I rearrange this equation, I get VCE divided by VBE is equal to minus GM RC. Okay, now we know that gain is equal to output upon input. Okay, so here this voltage gain AV is equal to VCE divided by VBE is equal to minus GMRC. It means this VCE is output signal and this VBE is input signal, and here this minus sign indicates that this output signal is 180 degree out of phase with respect to the input signal. Okay, now we know that this transconductance Gm is equal to collector current divided by thermal voltage. It means now this voltage gain is equal to minus IC RC divided by thermal voltage. Okay, so this is the equation of the voltage gain. Now look at this example. If you have a circuit where this DC base to emitter voltage is yielding a DC collector current of 1 milliampere, and for suppose here VCC is 15 volts and RC is 10 kilo ohms and beta is 100, and you have to find voltage gain. What would you do? In order to find this voltage gain, you will use this formula minus ICRC divided by VT. Here we know the value of collector current. It is 1 milliamperes, and we know that RC is 10 kilo ohms and the value of thermal voltage is 0.025 volts. After solving this, you will get minus 400 volts per volts. Okay, so this is your answer. Now we will understand the AC modeling. If there are AC and DC sources in your transistor configuration, then first you will do DC analysis, and for DC analysis all AC sources are short circuited. It means they are on, and if there is a capacitor, then this capacitor is open circuited. It means it is off. And next you will do AC analysis, and for AC analysis all DC sources are grounded, and if there is a capacitor then it is short circuited. It means it is on. All AC quantities depend on DC quantities, and the capacitor behaves as a short circuit for AC quantities and it behaves as an open circuit for DC quantities. Now there are two methods to model small signals. First is the hybrid pi model and the second is T model. First we will talk about the hybrid pi model. We know that the symbol of NPN transistor is like this, where this terminal is collector, this terminal is base and this terminal is emitter. So in case of the hybrid pi model, the equivalent circuit for small signal operation of bipolar junction transistor is like this, where this terminal is base and this terminal is emitter and this terminal is collector terminal. And as you can see here in this equivalent circuit, a current source is added here in this collector terminal. Okay, and this is the direction of collector current, this is the direction of base current, this resistance is R pi, and here we have voltage drop VBE. This terminal will be positive, this will be negative, and this is the direction of emitter current here, and here we have GM VBE, because we know that transconductance is equal to IC divided by VBE. It means IC is equal to GM VBE. Now here this current IB is flowing here. It means IB is equal to VBE divided by R pi, because we know that V is equal to IR. Therefore, I is equal to V upon R. Here V is VBE and R is R pi. Okay. Now what about this emitter current? It is equal to IB plus IC here, because we know that here this IE is leaving current and IB and IC are entering currents. So this is your hybrid pi model for NPN transistor. Now what about PNP transistor? We know that the symbol of PNP transistor is like this, where this terminal is emitter, this terminal is base, and this is collector. Now its equivalent circuit will be like this, where this terminal is base, this terminal is collector, and this terminal is emitter here. Now this direction of current source will be upward. Okay. Now here we have drop VEB. Now this terminal will be negative and this will be positive, and this resistance is R pi, and this source is GMVBE. Now here the direction of base current will be like this, and this is the direction of collector current here, and this is the direction of emitter current here. Okay. Now in this case this emitter current is equal to IB plus IC, because as you can see here this IE is entering current and this IB and this IC, they are leaving currents here. Okay. Now here, sorry, this is VEB. Okay, because in this case the drop is VEB. It means here this GM is equal to IC divided by VEB. Okay. So this is hybrid pi model for PNP transistor. Okay. Now for suppose if you have a transistor configuration like this, where the arrow is here, it means it is an NPN transistor configuration. Now here you have AC source and it is connected to a DC source. Okay, this is plus minus VI, and this is V, this is plus, this is minus, this is E, this is V, and this is C. Okay, so this is VCC, this resistor is RC, and this is RB. Now if you want to draw its equivalent hybrid pi model, because you know that this is a small signal model, it means it is an AC model, and we know that when we are doing AC analysis all DC sources are grounded. It means the equivalent hybrid pi model of this configuration will be like this. Okay, this is RB, this is RC, and since it is an NPN transistor, so the arrow will be like this. This is emitter, and we know that here it is grounded. Okay, this is VBE, this terminal is positive, this is negative, this is R pi, this is VI, and it is like this. Okay, this is GMVBE. Okay, and here we have IC, and here we have IB. Okay, and this IE is flowing like this. Okay, so this is an equivalent circuit for ideal bipolar junction transistor. Now, if you have a practical bipolar junction transistor, then in case of practical BJT, early effect is also considered, and in this case R0 is added in parallel to RC. It means here you will add R0 in parallel. This is R0, and we know that R0 is equal to VA divided by IC, where this VA is early voltage. Okay, so this is how you will start your analysis. First you will draw your equivalent hybrid pi model, and then you begin your analysis. Now look at this example. If you have a transistor configuration like this, it means there are both AC and DC sources here in this circuit, and if arrow is here, it means it is an NPN transistor configuration. And for suppose this DC battery is of 3 volts, this is an AC source, and here we have RB, which is 100 kilo ohms. This is RC, and it is of 3 kilo ohms. Here we have supply VCC, and for suppose it is plus 10 volts. Okay, here this emitter is grounded, it means it is at 0 volts. Okay, and you have to perform both AC and DC analysis here. So how you are going to solve this circuit? First we will perform DC analysis. We know that in DC analysis we find all terminal currents and nodal voltages. Okay, so its equivalent DC circuit will look like this, because we know that in DC analysis all AC sources are short circuited. Okay, here we have RC, here we have VCC, here we have RB, and here we have emitter. Okay, this is 3 volts. Okay, now first we will find nodal voltage at base VB. We know that VBE is equal to VB minus VE, and in forward biased condition this base to emitter voltage is 0.7 volts. Okay, and we know that here this emitter is grounded, it means it is at 0 volts. Okay, so it means nodal voltage at base is 0.7 volts. Okay, and nodal voltage at emitter is 0 volts. Okay. Now we will find base current. We know that this is the direction of base current IB. For this base current, we apply KVL in this loop and we start from this point. It means our KVL equation will be minus 3 volts plus IB RB plus VBE, because we know that voltage drop in this junction is VBE is equal to 0. Here we know that this RB is 100 kilo ohms and this VB is 0.7 volts. After solving this, you will get IB is equal to 2.3 divided by 100 kilo ohms, and after solving you will get 0.023 milliamperes. So this is your base current. Now we will find collector current IC. We know that IC is equal to beta IB. For suppose here beta is 100 and we know that this IB is 0.023 milliamperes. After solving this, you will get IC is equal to 2.3 milliamperes. Now we will find emitter current. We know that IE is equal to IB plus IC. Here IB is 0.023 milliamperes and IC is 2.3 milliamperes. After solving this, you will get IE is equal to 2.323 milliamperes. Okay. Now we will find nodal voltage at collector. We know that the formula of collector current is VCC minus VC divided by RC, because we know that this is our collector terminal where here we have VCC, here we have VC and here we have RC, and current IC is flowing in this direction. Okay, so it means VC is equal to VCC minus IC RC. Here this VCC is 10 volts, this IC is 2.3 milliamperes and RC is 3 kilo ohms. After solving this, you will get VC is equal to 3.1 volts. Okay, so now you have found all the terminal currents and all the nodal voltages. It means your DC analysis is done. Now we will start our AC analysis using hybrid pi model. Okay, so our hybrid pi model equivalent circuit will look like this, because we know that for AC analysis all DC sources are grounded. Here we have a current source, its arrow will be downward because it is an NPN transistor configuration. Here we have RC, this is the direction of IC. Here we have emitter, it is grounded, it is the direction of IE. This is RB, here we have R pi, here we have drop VBE, this is plus, this is minus, and this is VI. This is the direction of IB. Okay. Now, first we will find transconductance. We know that transconductance is equal to collector current divided by thermal voltage. In our previous slide, we have calculated this collector current, which is 2.3 milliamperes, and we know that thermal voltage is 0.025 volts. After solving this, you will get 92 milliamperes per volts. Okay, Now we will find R pi. R pi is equal to beta divided by transconductance. Here beta is 100 and transconductance is 92 milliamperes per volt. After solving this, you will get 1.09 kilo ohms. Now we will find Re. We know that Re is equal to alpha divided by transconductance. Here we don't know the value of alpha, but we know that alpha is equal to beta divided by 1 plus beta. Here beta is 100 and 1 plus beta will be 101. After solving this, you will get 0.99. So we put this value of alpha here. We know that transconductance is 92 milliamperes per volt. After solving this, you will get 10.8 ohms. Okay. Now we want to find voltage gain. We know that voltage gain is equal to output voltage divided by input voltage. Now first we'll talk about output voltage. We know that output voltage is present here in this region V0, and we know that here we have GMVBE. Now here we are considering that this is an ideal bipolar junction transistor. It means here we are neglecting early effect. So we don't add R0 here in parallel to this RC. It means here this output voltage is equal to minus IC RC. Okay. Now we know that transconductance is equal to IC divided by VBE. It means IC is equal to GMVBE. So we put this value of IC here. We get minus GMVBE/RC. Now we know the value of this transconductance, we know the value of RC, but we don't know the value of this VBE. We know that VBE is here in this region. So in order to find this VBE, we apply VDR here in this region. So our formula will be VBE is equal to R pi divided by R pi plus RB, and this term will be multiplied by VI. Okay. Now we know that the value of this R pi is 1.09 kilo ohms, and if we add this R pi and RB, we get 101.09 kilo ohms. Okay, and here we have VI. Now this kilo ohms is going to cancel this kilo ohms. So this VBE is equal to 0.011 VI. Okay, now we put this value of VBE here in this equation number 1. We get V0 is equal to minus GM multiplied by 0.011 VI multiplied by RC. Okay, now we know that this transconductance is 92 milliamperes per volts, and here we have 0.011 VI, and we know the value of this RC, which is 3 kilo ohms. Okay, so after solving this, you get V0 is equal to minus 3.04 VI, and it means V0 divided by VI is equal to minus 3.04, and we know that this V0 divided by VI is gain. Okay, so this is your answer. Okay, so now you have performed your AC analysis as well. Now look at this example. If you have a transistor configuration like this, where you have arrow here, it means it is an NPN transistor configuration. So this is VCC, and for suppose it is 10 volts, this is RC and it is 47 kilo ohms, and this is VEE and it is 0 volts. This is VI, means it is an input source. This is 100 kilo ohms and it is RB. Okay, and you have a capacitor here, and if beta is 100 and collector current IC is 0.1 milliamperes, and this collector current is flowing in this direction, and you have to find gain R pi and RE here. So how you are going to start your analysis using hybrid pi model? First you will draw your equivalent hybrid pi model circuit, which would be like this. Here we have a current source, and okay, now as you can see here, this capacitor is added and it is drawn in parallel here, and we know that for AC analysis this capacitor is short circuited. This is RC, this is an NPN configuration, so arrow will be downward. This is VBE GM, current IC is flowing in this direction. This is RB and current IB is flowing in this direction. This is R pi, this is positive, negative, this is VBE. Emitter is here and it is grounded, and current IE is flowing like this. Okay, so this is your equivalent hybrid pi model circuit. Now first we will find alpha. We know that alpha is equal to beta divided by 1 plus beta. Here beta is 100 and here we'll have 101. After solving this you will get 0.99. Now we will find transconductance. We know that transconductance is equal to collector current divided by thermal voltage. Here collector current is 0.1 milliamperes and thermal voltage is 0.025 volts. After solving this you will get 4 milliamperes per volt. So this is transconductance. Now we will find R pi. We know that R pi is equal to beta divided by transconductance. Here we know that beta is 100 and transconductance is 4 milliamperes per volt. After solving this you will get 25 kilo ohms. Okay. Now we will find Re. We know that Re is equal to alpha divided by transconductance. Here alpha is 0.99 and transconductance is 4 milliamperes per volts. After solving this you will get 247.5 ohms. Okay. Now we will find voltage gain. We know that voltage gain is equal to output voltage divided by input voltage. Here this output voltage is present in this region and we have input voltage here in this region. So this V naught is equal to minus IC RC, and this input voltage will be equal to IB RB plus IB R pi, because we know that this RB and R pi they are connected in series. Now we can write this equation like this: IB RB plus R pi, because we know that IB is present in both of these terms. So I took it out, and we know that IC is equal to beta IB. It means IC divided by IB is equal to beta. So we can write this equation like this: minus beta RC divided by RB plus R pi. Okay, here we know that beta is 100, RC is 47 kilo ohms, RB is 100 kilo ohms, and R pi is 25 kilo ohms. Okay, after solving this, you will get minus 37.6 volts per volts. So this is your voltage gain. Okay, now here is your class task. If you have a circuit configuration like this, okay, now here we have one base resistor, and here we have another base resistance. Here we have VBB, which is 9 volts. This is RB1, which is 27 kilo ohms. This is RB2, which is 15 kilo ohms. This is RB, which is 10 kilo ohms. This is VI, and here we have arrow. It means now this is an NPN transistor configuration. Now this is VCC, and it is also 9 volts. This is RC, which is 2.2 kilo ohms. Here this emitter is grounded, and here we have another capacitor, and here we have R naught, and for suppose it is of 2 kilo ohms. Okay, now you have to perform its AC analysis as well as DC analysis. It means you have to find all terminal currents and nodal voltages, and for AC analysis you have to use hybrid pi model. Okay, so this is your class task. That's all for today. Now, what are the key takeaways of this lecture? In this lecture, you studied about voltage gain. Here you also studied about methods that are used for AC modeling. You studied that there are two methods for small signal analysis or AC modeling. First is the hybrid pi model, and second is T model. In this lecture, you understood what is the hybrid pi model, and you also solved some examples.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.